Hello, Rouse. For lesson 2.5 on the quotient rule, I want to show you another approach to dealing with quotients. And it's actually the approach that our curriculum expects of us. Using this quotient rule, where we say that the derivative of quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared, isn't actually in our curriculum, and so we can't expect you to use it. Most students, I'll say it's an option for you to use it, and most students choose to use that option because the alternative isn't that great. I really don't understand why the curriculum doesn't include it. To show you what our curriculum documents expect of us, let's take a look at the examples from class, example 2 and example 3. Let's find a simplified and factored expression for delta y by delta x with natural exponents. If y is equal to the square root of x all over x squared plus 1. What our curriculum expects us to do is to take a step where we manipulate the function and we write it as a product of 2 powers, 1 with an exponent of -1, and then we use the product rule combined with the chain rule. I don't think it's a better or a faster approach, but it does, one advantage is that it does get us a little bit of practice with the chain rule, which is not a bad thing. So what I'm going to do is I'm going to show my steps on a product rule here, and I think I'll show my steps on the chain rule there as well. I'm going to take the derivative of the first, multiply that by the second, using square brackets there to make it clear what's being differentiated. To that, I will add the first. I'm going to write it with a fractional exponent to make finding the greatest common factor a little bit easier. Times, and I think I'm going to jump into my chain rule here. When I take the derivative of the second, you usually don't need to take another step to write that you're taking the derivative and then write a chain rule. If you just set it up like this, you want to take the derivative of this power of a function with respect to x. Well, you're going to create this chain. You're going to link this chain through the power of the base, or sorry, the derivative of the base with respect to x. So think of it as the derivative of a power of a function with respect to x is the derivative of the power with respect to the base multiplied by the derivative of the base with respect to x. And things should work out just fine. Okay. Imagine that we weren't showing our steps, then we could get started a little bit sooner. Let's take the derivative of x to the exponent 1/2, multiply that by the second, leave that first, multiply by the derivative of the outside. When you displace this negative exponent, let's make sure that we write it as a coefficient in brackets so that it's clear it's being multiplied and not subtracted. Get x squared plus 1 to the exponent -2, and then multiply that by the derivative of our base with respect to x. Be ready for questions that ask you to differentiate and not simplify. So you could stop here, I suppose. In this question, the intent was for us to come up with a simplified factored expression with natural exponents. But I'm going to take a step here. I don't see anything to do with this first term. I just want to tidy up here. I see some coefficients that can be multiplied together. I see some bases of powers on bases of x that could be, let's say, collected, simplified. And that's going to make my next step of common factoring a little bit easier. Let's see, I've got a +1 multiplied by a -1 multiplied by a +2. I have an x to the exponent 1/2 times an x to the exponent 2/2, be x to the exponent 3/2. And then I have x squared plus 1 to the exponent -2. Now let's remove our greatest common factor. Our greatest common factor, that's going to cause the most simplification here, is going to be the power of each base with the smallest exponent. This is a 2 to the exponent 1. This is a 2 to the exponent -1. 2 to the exponent -1 is smaller than, -1 is smaller than +1. So I'll remove a factor of 1/2. Common between x to the exponent negative 1/2 and x to the exponent 3/2 is going to be x to the exponent negative 1/2. Common between negative 1 factor of x squared plus 1 and negative 2 factors of x squared plus 1 is going to be negative 2 factors. It's the smallest number of factors that are in each expression. And if you're having a hard time seeing that this expression has negative 2 factors of x squared plus 1, just watch what happens when you remove the common factor. I'm going to use a large square bracket to draw my reader's eye to the fact that I am removing a common factor so that they're not saying, I don't get why this term changed to that and what happened to this binomial. Let's see, 1/2 divided by 1/2 is 1. X to the exponent negative 1/2 divided by x to the exponent negative 1/2 is x to the exponent 0, which is 1. X squared plus 1 to the exponent negative 1 divided by x squared plus 1 to the exponent negative 2. I'm going to keep my base and subtract my exponents. Here's me keeping my base. When I subtract my exponents, negative 1 minus negative 2, that's negative 1 plus 2, which is positive 1. We're using grade 9 power laws and integers here. I understand if it looks confusing because you don't have a lot of practice common factoring with negative or fractional exponents. But all we need to do is combine common factoring from grade 10 with rational numbers from grade 9. It can be simple when you get there. It takes a bit of practice. Negative 2 divided by 1/2 is negative 4. X to the exponent 3/2 divided by x to the exponent negative 1/2. I'm going to keep my base and subtract my exponents of 3/2 minus negative 1/2 is 3/2 plus 1/2 is 4/2, which is 2 wholes. And this factor divided by itself will leave me with a quotient of 1. So look at how our quotient has simplified. Our quotient now just has positive natural exponents on it. Okay. Let's see, I'm going to displace the 2 into the denominator. That'll be displaced in the denominator. This power with a negative exponent, I'll reciprocate and put its base in the denominator. So this is all that's going to remain in the numerator. I think I'm going to lead with a 1, finish up with a minus 3x squared. In my denominator, I'll see a factor of 2, a factor of the square root of x, and 2 factors of x squared plus 1, like that. Okay, that should be the same or very, very similar to what we came up with in class. The order of your numerator, I'm not too worried about. I don't like leaving leading negatives, which means I might feel the need to remove a factor of negative 1 from the entire numerator if I hadn't just settled on this rearranged order. Let's try example 3, which said given f of x equals 2x cubed minus 7 divided by x squared times x plus 1, we are asked to find f prime of 1. Even if I'm going to use this approach of multiplying by the reciprocal, I'm still going to use the same strategy to avoid a second product and distribute in my second factor. So I'm going to write this as the product of 2x cubed minus 7 multiplied by x cubed plus x squared to the exponent negative 1. Let's try this one without bothering showing the derivative rules. Should take fewer lines that way. F prime of x, I'm going to do the derivative of the first times the second plus the first times the derivative of the outside of the second with respect to its base times the derivative of the base with respect to x. So derivative of the first, 3 times 2 is 6x squared times the second, x cubed plus x squared to the exponent negative 1 plus the first 2x cubed minus 7 multiplied by the derivative of the power with respect to its base, x cubed plus x squared to the exponent negative 2, multiplied by the derivative of the base with respect to x, like that. Any concerns that I had about getting away from a factored form by performing this distribution, I think are alleviated by the fact that this question is just an arithmetic question. I think it would be a waste of time to do any sort of factoring or expanding or rearranging here. you have f prime of x. You want to find f prime of 1. So make x1. And show as much or as little substitution as you feel is required. I don't think it's a good idea to try to jump to the answer or even to try to type this into your calculator in one go. I don't think we need a calculator to do this question. But I do not expect you to show all substitution here. I think you can handle that 1 squared is 1 times 6 is 6. 1 cubed is 1. 1 squared is 1. 1 plus 1 is 2. The reciprocal of 2 is 1/2. Then I've got 1 cubed is 1 times 2 is 2 minus 5 is -5 times -1 is +5. I've got 1 cubed is 1 plus 1 squared is 1. 1 plus 1 is 2. The reciprocal of the square of 2 is 1/4. And here we have 1 squared is 1 times 3 is 3 plus 2 times 1 is 5. So we get, what, 3 wholes plus 25 quarters, which is 25 quarters plus 12 quarters, so 37 quarters, which is the same answer that we got when we used the old fashioned, or the new fashioned, I don't know, quotient rule in class. I don't plan on forcing you to use this idea. If I give you a function where there already is a negative exponent, you could take the initiative and write it as a quotient. I think you should try it this way a couple of times, just so that you keep getting practice of the power of a function rule, because that's a more challenging rule, I think, than the quotient rule.